Uh, Hello everyone, my name is Piotr Skowron and together with Dominic Peters, we'll be giving today's tutorial on proportionality-based fairness in social choice. So here is the outline. We are going to go through three main models where proportionality is an important question. The first one is apportionment, where we ask how to divide how to divide seats between political parties in a parliament. The second one is committee elections, where we ask how can we select a body that would be representative towards the voters. But here, differently to the other settings, we do not ask the voters to vote on political parties, but rather on individual candidates directly. And the third model is participatory budgeting, where the citizens, through voting, decide how to spend a part of the municipal budget. So basically, we are these models can be arranged in a hierarchy going from the least general to the most general, and the question related the question how to define proportionality and how to achieve it will become much more and more complex. So it will be very intuitive and easy for the apportionment setting, and it will be it will require a couple of ideas in the setting of committee elections, and these questions will become, let's say, the most challenging and most interesting in the context of participatory budgeting. And why do we care about proportionality? Basically, we care because we would like to be fair towards groups of voters, and we would like to be fair towards these groups of voters, not looking at the attributes of those voters, but we would like to look only at how these voters vote, and to ensure that each group of voters who vote similarly is treated proportionally, is given some proportional amount of utility, of power, proportional to the size of this group. We would like to ensure exactly that the voters have equal power of voting, that we would like to ensure that we are not ignoring minorities of voters, for instance, that we do not follow the idea of majority voting, and we would like to select committees or to select outcomes in participatory budgeting in such a way that all different viewpoints of the voters are equally represented. So let's start with the model of apportionment, where we have M political parties, and the voters vote for these political parties. Each voter votes for a single political party. So let an I denote the number of votes cast on party PI. So let's assume that our goal is to select K members of the parliament. So we have K parliamentary seats that we would like to divide them between the political parties. So how to do that? In some settings, it's very, very simple. So for instance, let's assume that we have the following number of votes. Party 1 gets 10 votes, party 2 gets 20 votes, party 3 gets 20 votes, and so on and so forth. And so what we can see here is that if our goal is to select K members of the parliament, then then it is quite straightforward, and we should give 1 seat to party 1, 2 seats to party 2, 2 seats to party 3, and 5 seats to party 4. This way, the number of seats allocated to each party is proportional to the number of votes cast on this party, and this is why we say that this outcome is proportional. However, not all instances of apportionment are so nicely aligned. For instance, in this second example, we can see that the outcome that we would truly believe that would be proportional would not be integral, right? So we would like ideally to give 0.6 seats to party 1, 0.7 seats to party 2, and so on and so forth. So we would like to make this this solution integral, and this is where the question of how to do it, how to achieve this proportionality becomes interesting. So we could do it like that, for instance, allocating 0 seats to party 1 and 1 seat to party 2, and so on. Or we could do it in this way or in that way. And in fact, all these allocations could be viewed as proportional. And in fact, different methods of apportionment, which are used by countries, for instance, would return these different results for this particular instance. So how we can formally basically how we can formally reason about proportionality in such setting. So we can define axioms. And an axiom would, for instance, the natural axiom of proportionality would be what is called a lower quota. And it says that a party pi should get at least k times ni divided by n seats. So in this example, basically, it says that, okay, the lower quota for party 1 is 0, for party 2 is 0, for party 3 is at least 3, and for party 4 is 4. So this means that these parties should get at least the following number of seats. Naturally, we can define analogously an upper quota, which is a ceiling from the same fraction, and then we say that an apportionment solution satisfies an upper quota if each party does not get more than this quota defined by in this way. Okay, so having these quotas gives us a natural way to define an apportionment method. For example, we can first assign to each party its lower quota, and then look at the reminders, and go by these reminders and allocate one more seat to some parties, and starting with those which have the highest reminders. For instance, let's have a look how this would look like in this example. So first, we allocate lower quota, that is 0, 0, 3, and 4 seats to the parties. So we allocated in total 7 seats. Now the reminders are 0.6, 0.7, 0.9, 0.8. So we can see that the largest reminders corresponds to party 3. So this party gets one additional seat. Next, the largest reminder is for party 4, so it gets one additional seat, and we have still one additional seat, and it goes to party 2 because it is the next largest reminder. So in total, we have that party 1 gets 0 seats, party 2 gets 1 seat, party 3 and 4 get respectively 4 and 5 seats. Okay, and this is this method, the largest reminder method, also called the Hamilton method, satisfies those two axioms, lower and upper quota. However, it fails some other axioms that you might find important. For instance, it fails the axiom of house monotonicity. So what house monotonicity says is that basically, if we increase the number of seats in the parliament, then none of the parties should be harmed. So if a party got certain number of seats, then after increasing the total number of available seats, then this party should get at least the same number of seats or more. The largest reminder method unfortunately fails this axiom, which is often referred to in the literature as the Alabama paradox. And this example illustrates how this happens. So if we have 10 seats, then we can see that party 1, 2, and 3, which got respectively 6, 6, and 2 votes, get 4, 4, and 2 seats. However, if we increase the number of seats to 11, then the results changes, and we can see that party 3 starts getting now one only seat. As a result of increasing the total number of seats, party 3 gets fewer seats in the parliament, which shows that the house monotonicity is failed. Okay, so another way to achieve lower quota is and to achieve house monotonicity at the same time is by following the idea of the don't method. And here we basically iteratively assign seats to the parties. And how we do it? We do it in such a way that the ratio ni divided by si of r plus 1 is maximized, where si of r is the number of seats which the party I already got up to this moment. So let's have a look at this example once again. How we can iteratively explain this, how we can visualize this process. So we can think of filling a table. First, in the first row, we fill just the number of votes cast on the course on respective parties. In the second row, we divide these numbers of votes by 2. In the third row, we divide it by 3, and so on and so forth. So we have this table, and we simply pick k largest values from this table. And each value, if we pick each value, then this corresponds to giving a seat to a corresponding party. So in this example, this means that party 3 gets 4 seats, and party 4 gets 6 seats, and the parties 1 and 2 get no seats in the selected parliament. Okay, so since we do it iteratively, then clearly we can see that this method satisfies the house monotonicity. However, maybe it is not clear that it satisfies lower quota. So maybe let's have a look at the very short proof, which illustrates why this method indeed satisfies lower quota, and this will be illustrative and this will help us also to understand the intuition behind the more complex rules for committee elections. So towards a contradiction, assume that there is some party PI, let's call it, that gets less than the desired number of seats. So by pigeonhole principle, we know that there must exist also a party PJ that gets more than the required fraction of the seats. So let's consider the iteration in which this party PJ gets its last seat, and we will show that by the don't method actually would prefer to give these seats to the party PI rather than to party PJ. Indeed, how we can show that? So we can estimate the values of Si in this round R. So Si of R, we know that this is lower than this, strictly lower than the lower quota for this party, and this means that since this is strictly lower, then this must be then this is lower or equal than this lower quota minus 1, and we can skip the floors and get the following estimation. For Si of jar, for Sj of R, since we took the iteration R as the one where the party PJ gets its last seat, then we know that Sjr is actually lower by 1 from the Sjr plus 1. That is from the number of seats given to this party in the following round. So this is we get the estimation that this is greater than k times nj divided by n minus 1. Okay, and then when we compute these ratios, then we can see that for party I, this ratio is greater or equal than n over k, and for party J, this ratio is actually strictly lower than n over k. So this gives a contradiction, since the don't method assigns seats to a party with the highest ratio, and in this case this would mean that it would prefer to give the seat to party I rather than to party J in this round R. Okay, so that was the apportionment method model, and the model of apportionment is kind of simple, and there the concept of proportionality is rather intuitive. And now we will move to the model which is a bit more complex, but somehow related to the model of approval-based elections. And here the goal is to select k candidates. That is, we have a fixed number of seats that we would like to give to some candidates, but now the voters do not vote for political parties, but rather for individual candidates. And let's have a look at first why this model is very similar to the model of apportionment. So in this simple example, we can see that the votes are very well aligned. So for instance, voter V1, V2, V3, and V4, they vote exactly on the same candidates. V5, V6 also vote on the same candidates, and V7 and V8 also vote for the same candidates. So I will use two different kinds of representations to illustrate these preference profiles. The one on the left hand side basically lists the votes cast by the voters. So these are basically the votes. These are for each voter we list the candidates which are approved by this voter. And on the right hand side of this picture, we can see that there are blocks, and those blocks they correspond to the candidates, and each block corresponding to a candidate is aligned in such a way that the voters below this box basically approve this candidate. So we can see that, for instance, these are the two equivalent representations of the same profile. And we can see here that indeed those votes are nicely aligned. So we can in fact group the candidates in some sets that would correspond to political parties. So indeed we can see that, for instance, if we consider the green, the red, and the green and the blue candidates, those four candidates approved by voter V1, V2, V3, and V4 as a single party, then we could say that voters V1, V2, V3, V4 actually voted for this party A. And then indeed we could transfer the ideas from the literature on apportionment to this model and to see and say what does it mean to be proportional. However, what is more challenging is how to deal with more complex elections where these votes are not so nicely aligned, like in they do not have this structure that would resemble party list profiles. So, for instance, here we can see that that we cannot even nicely draw this picture, for dealing basically with this kind of profiles, we need to somehow extend the ideas from the apportionment. So how to do that? So let's move back. So now I will define two rules which follow the two different ideas, but which origin in ideas that started in Scandinavia in the end of 19th century. And these rules they behave particularly well with respect to proportionality. So let's start with the first rule, which was defined by Thiele and which is currently known under the name of proportional approval voting. So basically, this rule it follows the idea of maximizing certain score, and how this score is computed. So let's assume that we have a committee W, and how to define the score for this committee. So basically, whenever a voter V approves certain number of candidates from this committee W, let's say T members of this committee W, then we assume that this voter assigns the score of 1 plus half plus 1/3 up to 1/T to this committee. So, for instance, let's have a look at this at our running example. Here, assume that our goal is to compute the score of this committee that consists of the green lady, the red guy, and the blue guy. So we can see that voter V1 approves two members of this committee, namely the green lady and the red guy. So this voter assigns 1 plus half points to this committee. Voter V2 also approves two members of this committee, so it assigns 1 plus half. Voter V3 actually approves all three members of this committee, so it assigns the score of 1 plus half plus 1/3, and so on and so forth. And in total, this committee gets 8 plus 5/6. This is the score that this committee gets. So basically, to compute the outcome according to proportional approval voting, we need to look at every possible committee of size K and for each committee compute the score as using this definition, and to pick the committee with the highest score. So we can see that this rule is defined in a way that we compute the outcome solely based on the information of what of welfares of the voters, of how well the voters find the how good the voters find the outcomes. So formally, what does it mean? We can say that the rule is welfarist if the decision is made only on the welfare vector. And what is a welfare vector? This is a vector with one coordinate for each voter, and the if coordinate corresponds to the number of members of the committee which are approved by the voter. So for instance, if I am the voter and I have, let's say, approved 7 members of the committee, then my welfare is 7, and this vector has number 7 on the position that corresponds to me as a voter. And so basically, if we make a decision solely based on the satisfaction of the voters from the committees, then we say that the rule is welfarist. Okay, and the second rule follows a different idea. Second rule it was defined by Fragments, and this is a rule which is based on the idea of earning money and buying for this money, buying the candidates. So we can assume that the voters earn money with a constant speed. It doesn't matter, but we can, for the sake of concreteness, we can assume that this is $1 per time unit. And in the first moment when the voters, there is a group of voters, called this group S, who have in total N dollars collected, and who all approve not yet selected candidate C, then what we do is then we say that these voters, as soon as they have money, then they greedily buy a candidate. So here we implicitly assume that buying a candidate costs N dollars. So we add, in such a moment, we add C to the committee, and we make the voters from S pay for this candidate, which corresponds to resetting their budget to 0. So let's have a look at this example and see how this rule would work. Recalling the notation, here we can see that the candidate C1 is approved by voters V1, V2, V3. Candidate C2 is also approved by V1 up to V3, C3 as well. Candidate C4, C5, and up to C15, each of them is approved by a single voter. For instance, C4 is approved by V1, C13 is approved by V4, and so on and so forth. So how does it work? Let's assume that our goal is to select 12 candidates. So the voters start with the budget equal to 0, and they start earning money. And we can see that in time t1 equal to 2, voters V1, V2, V3, they have earned in total $6. So buying a candidate in a committee costs $6. So they have money that allows them to buy the first candidate, which could be C1, C2, or C3. This doesn't matter, so this is subject to tie breaking. So let's say that C1 is bought in the first round. So now these voters, they get rid of their money, and the rule starts, and the time resumes. The rule resumes. So after 2 additional time units, those voters have collected once again $6, which allows them to buy a second candidate. Here is C2. After the next 3 steps, another candidate is bought, that is C3. Actually, after the time, at time 6, we can already see also that voters V4, V5, and V6, each of them has collected already $6, which is enough to buy one candidate. So for instance, V4 might buy C7, V5 might buy C8, and V6 might buy C9. And then the time resumes once again, and in time 12, all these voters have once again earned $6, which allows them to buy one additional candidate each. So we have selected 12 candidates, so the rule stops, and basically this is the committee that would be selected in this example by the fragments rule. Okay, so we have these two rules, PAV and the fragments rule. So now the question arises: which of these rules is better, and basically whether any of them is good, whether any of these rule is proportional, and if which of those two should be preferred. So basically, we can see that they indeed behave slightly differently. And in this example, we can see that the fragments rule, the outcome returned by the fragments rule is given in the left-hand side, and by proportional approval voting in the right-hand side. So which of them is more proportional? So it's maybe not really clear at the very beginning, but I will try to explain the ideas that are behind the two outcomes and the two rules. So for the fragments rule, we can see that the voters are nicely aligned, and the voters V1 up to V3, they approve different candidates from V4 up to V6. So we can say that since voters V1 up to V3, they form half of the society, they should be allowed to decide about half of the committee members, right? So here it makes sense to give them 6 candidates, to give them the right to decide about 6 candidates, and the remaining half of the voters V4 up to V6 should have also the right to decide about half of the members of the committee, that is about 6 candidates. For PEV, on the other hand, since the PEV is the welfarist rule, it identifies that actually by removing candidate C6 and adding candidate, say, C13, we would decrease the total inequality in the outcome, in the satisfaction of the voters. So one voter would its satisfaction would decrease from 4 candidates to 3 candidates, and for the other voter, their satisfaction would increase from 2 to 3. So, and by following this idea, also C5, C4 would be removed, and C14 and C15 would be added. And actually, the committee on the right-hand side would be the one that minimizes the total inequality in voter satisfaction, and the one that maximizes the PEV score. Okay, and so we can see that all these outcomes can be viewed as proportional, but with certain kind of interpretation. However, how to make this interpretation more formal? And now I will speak about the axioms that we can define to capture these two types of proportionality. Okay, so the first approach is to define axioms for what is called cohesive groups. Let me explain this through the following example. So we can say, let's assume that here our goal is to select 4 candidates. Now we can see that this group, V1 up to V4, they form half of the society, so they should be given half of the committee members, the right to decide about half of the committee members, so about 2 candidates. And additionally, there are 2 candidates on which they agree. So ideally, we would like to say that indeed those voters by their size should have right to decide about 2 committee members, and there are 2 candidates that they actually agree, so this is feasible for them to give their right to decide about these 2 committee members, right? So here, analogously, this group of voters, they form 1/4 of the society, and they also agree on at least 1 candidate. Actually, they agree on 2 candidates, but it doesn't matter. So this means that this group should have the right to decide about 1 candidate. Now, what does it mean to decide about about 1 candidate, or to decide about 2 candidates? So ideally, we would like the following definition: that each group of voters with at least L times N over K voters. So once again, N is the number of voters, K is the size of the committee. So basically, N over K, this is the number of voters that should be eligible to, should be allowed to decide about 1 candidate, should be given the right to decide about 1 candidate. So L times N over K, this is the number of voters that should be given the right to decide about L candidates. And if they approve some L candidates, then they should, on average, in the outcome, should have at least L representatives. This means, what does it mean, L representatives? That they should, on average, approve L members of the elected body. So, for instance, this group, this means that they should, on average, approve at least two candidates, and uh, and uh, and this should hold for each group of voters. So this is ideally what we would like to have. However, is it possible? Unfortunately not. This is illustrated by the following example with 12 voters and 3 committee members. So for instance, here this would mean that the voters V1 up to V4, they form 1/3 of the society and they agree on one candidate, namely A. So according to this definition, they should be eligible to at least one candidate, on average, which means that that candidate A must be selected. The same reasoning applies to voters V4 up to V7 would give us information that B must be selected, and when we apply the same reasoning to the group of voters V7 up to V10, then we get that also C must be selected, and applying this to V10 to V12 and V1, we get that also D must be selected, so we must select A, B, C, and D. However, the size of the committee to be selected is only 3. So this example shows that actually we cannot satisfy this axiom. However, this axiom can be slightly only relaxed so that it is satisfiable. So now we can relax this axiom by requiring that this group of voters who intuitively should get L candidates has now the right to decide about L-1 representatives. That is, they have on average L-1 candidates that they approve in the elected body. And this relaxed property is already satisfied by PAV, which is a very strong indicator that PAV indeed satisfies, is a proportional rule. What is interesting is that Fragment's rule would satisfy a more relaxed version of this property, namely when we replace, if we replaced L-1 by L-1 divided by 2. So in a way, when viewing from this perspective, we could say that Fragment's rule is, let's say, half as proportional as PAV. Okay, so how we can define these concepts formally? First, we need to define what is a cohesive group. And an L-cohesive group is a group of voters which is of size at least L times N over K. And that is the groups which agrees on at least L candidates. That is the intersection of their approval sets is of size at least L. And the proportionality degree, we can say that the proportionality degree of a rule is F, where F is the function kind of this L. Where for each L cohesive group, we have this guarantee that the average number of candidates approved by these voters from the group S is at least F over F of L. So we can so what we have said before is that PAV has the proportionality degree of F of L equal L-1, and for the Fragment's rule, F of L would be L-1 divided by 2. A similar axioms that is maybe a similar axiom in the spirit, but not quantitative, but rather qualitative, is extended justified representation. And basically, extended justified representation, in short, EGR, says that an outcome W satisfies this axiom if for each L cohesive group of voters, there exists one voter in this L cohesive group that approves at least L members of the elected committee W. A weaker variant of extended justified representation is proportional justified representation, where we do not require that there is a single voter who approves at least L members of the elected body, but rather we would require that in total, this group of voters S approve at least L different members of the elected body. So clearly proportional justified representation is weaker than extended justified representation. And the weakest form of this, weakest from these axioms is the simply justified representation, where basically do not care about large cohesive groups, but we only say about one cohesive groups. So if there is a group of n over k voters who approve at least one candidate in total, then there must be a voter who approves at least one candidate. Okay, so we can see that these axioms can be arranged in some hierarchy. EGR is stronger than PGR, and PGR is stronger than JR. Actually, PGR, it can be shown that it implies the behavior that it implies the lower quota, the axiom that we know from the literature on apportionment and from the previous part. So when these candidates are so nicely aligned that they can be grouped into sets which resemble political parties, then on these nicely aligned profiles, PGR would imply that the rule must satisfy the axiom of lower quota. And also EGR implies the proportionality degree of L minus 1 divided by 2. That is the one which is satisfied by frag main. And what is interesting that frag main actually satisfies this proportionality degree of L minus 1 divided by 2, which is tightly implied by EGR, but does not satisfy EGR itself. And for PAV, actually PAV has higher proportionality degree and also satisfies the axiom of EGR. So at first we can say that our feeling is that maybe PAV is a more proportional rule. However, actually, we can define other axioms which try to capture this idea of not proportionality with respect to welfare, but rather this notion of proportionality with respect to power. And one of these axioms is called priceability, and the intuition is that the axiom of this axiom is that the voters should be able to buy the candidates by the money that we will give to them. And the idea of why this is fair comes from the fact that each voter is given initially the same amount of money. So basically they have the same voting power in a way expressed by the or maybe defined as the number of or as amount of money that they can use for buying candidates. And formally, a price system is a pair where P is a price, and for each voter we also define the payment function, which specifies how we can define which specifies how the voters pay for the candidates which are bought. And these payment functions must satisfy the following two criteria. A voter can pay only for the candidates that she approves, and a voter can spend at most $1. And we say that the price system supports a given committee if for each candidate that is selected, that is member of this committee, the total amount of payments given to this candidate sums up to the price P, and no candidate outside of the committee gets any payment. And also there is a third condition which says that the voters do not have additional sparse money that can be used for buying an additional candidate. So in total, there's no group of voters who support the same candidate and who have in total more than P dollars since they could spend this money on buying a candidate. For instance, here we can see that in this example, we can see that the outcome returned by fragments rule is indeed priceable. In this example, for instance, voter V1 would pay $1/6 for candidates C1, C2, and C3, and $1/2 for C4, and the price would be exactly half of the dollars. And these payments here would indeed satisfy properties outlined in the previous slides, which shows that that indeed the outcome returned by the fragments rule, this particular outcome is priceable, and in general, fragments rule satisfies this axiom of priceability. And priceability implies PGR, however, it's not comparable with EGR. So actually, fragments rule satisfies priceability, but PAV does not satisfy priceability. And we can also show that no welfareist rule, that is no rule which is based on this distribution of satisfaction of the voters only, would satisfy the axiom of priceability. So this indeed shows that this axiom, basically, they describe kind of a different, very different behavior and very different general ideas behind the rules. Also, there are other criteria which are important for those rules, which do not relate to proportionality. For instance, PAV is Pareto optimal, and fragments rule satisfy this axiom of House monotonicity. That is, if we increase the committee size, then the candidates which have already been selected remain selected, and we additionally select a certain number of candidates, missing candidates. And in some settings, actually, these axioms are also important. So basically, it's what we can say that we have two good proportional rules. One is PAV and the other is fragments rule, and they implement slightly different kinds of proportionality, which are expressed by these different types of axioms, and also they satisfy different types of other criteria which are often important. And the last concept that I would like that pertain to proportionality that I would like to mention is the core. And basically, core is the strongest, is stronger than EGR. And the idea here is the following. So the group of voters, which is of size L times n over k, should be once again allowed to decide about L candidates. But now we do not have this requirement of cohesiveness, but rather we say that a group should not deviate from the solution of W. What does it mean that it should not deviate? This means that this group of voters should not be able to propose these L candidates so that each member of the group S would be more satisfied with this proposed set rather than with the original set. So formally, we can say that there should not exist a group S such that they can propose a set of candidates T, which is proportionally smaller. So for instance, if the set S of voters is 30%, consists of 30% of the society, then set T that they propose should also consist of 30% times K of candidates. And if they can propose this set of T so that each voter from S would prefer T over the original set W, then we can say that they can deviate. And if no voters can deviate, then we say that the outcome is in the core. So for instance, here we can see that this outcome returned by PAV is not in the core because these voters V1 and V2 up to V3, they are eligible, they should be allowed to decide about half of the committee, that is about 6 candidates. And indeed, they can propose candidates C1, C2, C3, C4, C5, C6, so that each of these members of these voters would be more happy with the proposed outcome than with the original outcome. So this shows that the outcome is not in the core. And actually, it's interesting to see that the core, being in the core, contradicts the Pigou-Dalton principle. And the Pigou-Dalton principle is this principle which is very typical for the welfarist rules. That is that the Pigou-Dalton principle says that it should not be possible to take two voters and to slightly decrease the satisfaction of one voter, slightly increasing the satisfaction of another less satisfied voter, because then it would be like a transfer of utility that would that would decrease the total inequality in the society. So basically, the Pigou-Dalton principle says that such transfers should not be possible, and this example shows that if we want to have the Pigou-Dalton principle, then we do not have the core. And what is interesting is that PAV gives the best possible approximation of the core subject to Pigou-Dalton principle. So if you would like to have Pigou-Dalton, then basically from the welfarist rules, basically PAV gives the best possible approximation of the core. And the core indeed is stronger than EGR. However, it's not comparable to priceability. And there is also more axioms that have been defined in the literature, like FJR, stable priceability, perfect representation, and so on and so forth. So unfortunately, I do not have time to go through all of them. However, if you are interested, I'm Also, I can also recommend a very recent book by myself and by Martin Lackner, which basically gives a more thorough description of these axioms and of this taxonomy. However, what I like to mention finally is that the question of the concept of core is still in a way understudied, because there are still important open questions that relate to this concept. First of all, the question that I find most important is that whether there exists an outcome, there exists a rule which always selects an outcome in the core. In other words, whether the core is always non-empty. This is a question that is open. And also, since this is not known, people started to also come up with other concepts which relate directly to approximation, for instance, to other types of relaxation of the core, and the natural questions that are still there is how close, if the core is not satisfied, how close is not possible to be satisfied always, how close we can get to the core through providing some relaxations like an approximation. Okay, so I will stop here. Thank you very much for your attention, and the remaining part will be given by Dominic Peters, and he will tell us more about the more complex domains like participatory budgeting.